Hello everyone, welcome to Numerical Methods class. In this class, we are going to talk about Chapter 2, Programming and Software. Let's start with the packages and programming. So there are two types of software uses. Actually, for the packages and programs or software can be used interchangeably for anything that utilizes some code, some methods behind it, and gives us some results. And users can use these kind of packages or software in two types. Let's say, first of all, the users who use what is given in the software. That means that we have a ready software with existing numerical methods embedded in it or coded in it. We can just use these existing ones to be able to find solutions. For example, in MATLAB or Excel, it is very straightforward to solve a system of equations or to generate a plot of XY values. However, this kind of use limits the capabilities. If we want to use this package for something which cannot be solved by the existing codes in the software, then we will have a problem. Then the second type of user comes into place, the users who develop macros or code files to extend the software capability. So this way we can actually extend the capability of software. Also, we are able to solve our problems which cannot be solved by the existing codes or programs in the software. So as engineers, we should not be tool limited. So we shouldn't be only using the tools, but should be able to develop those tools as well. And it is important that they should be able to do both. In other words, the engineers should be able to do both use the software and develop the software. That's why they should learn to write programs and develop ways to solve their problems. And in this numerical method class as well, we will develop our own codes, for example. These can be existing in MATLAB or Excel, or you can simply develop which doesn't exist. Develop some codes which don't exist in the software. Also, let's define the computer programs. A computer program is a set of instructions that direct the computer to perform a certain task. And there are some high-level computer languages such as Fortran 90 and C, which have rich and complex capabilities. And most engineers only require the ability to perform engineering-oriented numerical calculations, and that's why maybe this kind of Fortran 90 and C programs may not be necessary, and maybe only software which can perform engineering-oriented numerical calculations can be useful. For this reason, we can use a lower-level computer language such as MATLAB, for example. So we already have some existing functions in MATLAB which don't exist in Fortran 90 and C. So in other words, in MATLAB, there are further developed codes working behind as functions, and these are actually coded before we use and they are ready to use for us. But for Fortran 90 and C don't have those kind of functions or approaches. That's why we need to develop our own codes for these software. And this kind of engineering-oriented numerical calculations can be limited into the following 6 categories, and we narrow down the complexity to a few programming topics. First of all, simple information representation. These are like constants, variables, and type declarations can be defined, such as x equals 5, for example, which is a constant, let's say, or the mass is equivalent 68. Somehow these are simple informations. Also, advanced information representation is the second one. Data structure, arrays, records, these can be defined such as matrices, and mathematical formulas, assignment, priority rules, integrating functions. We can define these. Input and outputs. The fifth one is logical representation such as sequence, selection, repetition. We will talk about these in the following slides anyway. And modular programming, functions and subroutines. So the first 3 or 4 can be easily done, but these 5 and 6 we need to think about these while working on the first 4 to be able to have an organized computer code. So when we are writing codes or doing programming, it's actually easy to do that by just typing the numbers and words that we know to be able to develop the code. But it is important to have a structured programming, which means that a set of rules that prescribe good style habits for the programmer. And this is important because with a well-structured algorithms, we can easily share the code, and the shared person can easily understand it. If it is not well structured, it may not be understood well, and it can be complicated to be able to use it. And it is easy to debug and test, and it requires a shorter time to develop, test, and update. And a key idea behind this structural programming is that any numerical algorithm can be composed using three fundamental control structures: sequence, selection, repetition. And these are called logical representations. And these are important to be able to have a structured programming, and we will talk about these in detail in the following slides. Also, we first develop algorithms before developing the codes. That's why the demonstration of the algorithm is important, and they are represented by two approaches. First, flowchart, second, pseudocode, and we will talk about these in the following slides as well. These structures help the resulting computer code be clearer and easier to follow, and this way we can present a well-structured programming in our development process. Let's talk about the demonstration of the algorithms. First, the flowcharts. A flowchart is a visual or graphical representation of an algorithm. We simply use some charts to be able to show the process of the algorithm, and it employs a series of blocks and arrows, and each of which represents a particular operation or step in the algorithm. And the arrows represent the sequence in which the operations are implemented. And over here, you can see some symbols and the names of them, which represents some functions during the demonstration of an algorithm as a flowchart. So, for example, this symbol means it's a terminal, which represents the beginning or end of the program. These are the flow lines, like arrows, which shows the flow of the algorithm. And this is a rectangular prism, for example, shows the process. The calculations or data manipulations are written inside of this. If we have a parallel rectangular prism like this, it shows the inputs and outputs of data and information. And if we have a diagonal shape, and inside we show a decision, a comparison, a question, a decision that determines alternative paths to be followed. And a circle is a junction, which represents the confluence of flow lines. And there is this kind of shapes to the bottom, to the left, for example. Off-page connector represents a break that is continued on another page. And also to the left, count control loop, used for loops that repeat a specified number of iterations. Another representation scheme for the algorithms is pseudocode, and a pseudocode uses code-like statements instead of the graphical symbols of the flowchart. Basically, we don't use any shapes, but use some statements, like actually coding. And we have adopted some style conventions for the pseudocode in the book or in this class. For example, keywords such as if, do, input are capitalized. So the beginning, for example, here there's an example. These kind of things are capitalized. And the conditions, processing steps, and tasks are in lowercase. Actually, in the middle of the capitals, there are lowercase statements. And the processing steps are indented. So there is a process over here between if and else. So this one is indented, as you can see here. And keywords form a sandwich around the steps to visually define the extent of each control structure. And with these ideas, concepts, we can develop pseudocodes easily and have the demonstration of the algorithm. So as we said earlier, both the flowcharts and pseudocodes are demonstration ways of algorithms, and let's compare them over here. For example, on the left hand side, you can see a flowchart with a condition. If it is false, it goes to a block. If it is true, it goes to another block, and in the end, it finishes. So we can define this as a pseudocode, as you can see here, with if and else statement, because this condition basically if and else, and if it is true, a true block. If it is false or else, it is a false block, and if finishes it over here. So both the left and right hand sides are two different demonstrations of the same algorithm. So there are some advantages and disadvantages of these demonstration ways. First of all, the advantages of pseudocode. Pseudocodes are easier to develop a program with pseudocode because they are simply just statements, and we can easily write this down to the necessary software and easily have the developed code actually. But in the flowchart, we need to be able to understand if this is an if statements and try to write these. Also, pseudocode is also easier to modify and share with others, and so that this is a generalized way and it can be just shared with others, and they can also write their own codes. Also, there is advantages of flowcharts. The flowchart is better for visualizing a complex algorithm because it's kind of a graphical form. So if you want to demonstrate or present some algorithm to somebody else as a presentation or a visual representation, it's better to use flowcharts. But if you want to type in the codes and show how to type the code, then a pseudocode is a better way. And in this course, we will use the pseudocodes as the principal vehicle for communicating the algorithms, and we will also use the flowcharts for demonstration purposes.